Hi. Section is 7.2, trigonometric integrals. 7.3, there we go. Oh, because I didn't start. All right. Hello and welcome back to Calculus 2, section 7.3, trigonometric integrals. I guess the hype is necessary. You are supposed to memorize trigonometric pairs for calculus, and you are supposed to know basic integrals for derivatives, basic integrals and derivatives for trig functions. And you're supposed to know a whole bunch of trig identities already. What we're going to do, we're going to take all of that right now and come up with maybe a little systematic way of getting these more complicated trig integrals there. U sub is there. Extremely frequent. Almost every problem is going to be U sub in some form. And a lot of power reducing formulas, a lot of double angle and all of that kind of stuff. So we start with reviewing the table of basic integrals. I'm going to say that we're going to start with the trig pairs. So trig pairs are sine with cosine, tangent with secant, and cotangent with cosecant. So those are the pairs. And what that means is that the derivative of sine x is cosine x, which leads to integral of cosine x dx is sine x plus c. The derivative of cosine x is negative sine x, which means that the integral of sine x dx is negative cosine x plus c. The derivative of tangent x is secant squared x, which means that the integral of secant squared x dx is tangent x plus c. The derivative, that's halfway. The derivative of cotangent x is negative cosecant squared x, which means that the integral of the cosecant squared x dx is negative cotangent x plus c. The last two lines, d dx, so derivative of secant x is secant x tangent x, integral of secant x tangent x dx is secant x plus c. The last line, the derivative of cosecant x is negative cosecant x cotangent x, and the integral of cosecant x cotangent x dx is negative cosecant x plus c. Try to fit them all on the same page. If you look at these carefully, you are going to see patterns. If you don't know these yet, you must know them by Monday. And these formulas are extremely symmetric. If you look at this, sine goes to cosine, cosine goes to negative sine, but sines and cosines are together. Here's your tangent, secant, right pairs, and then cotangent, cosecant, cotangent, cosecant. Now look, tangent, cotangent, secant squared, cosecant squared, right? Secant, cosecant, secant tangent, cosecant, cotangent, right? They're highly symmetric because each of these is like a pair, pair, and the results look the same, except they use their own pairing. Further, every co is always negative, right? Cosine, cosecant, cotangent, they're all negatives. And the ones that are not co are positive. So there are systematic ways to remember this. And a lot of these will be, all of these will be utilized in a section. Now, we are only going to focus on sine, cosine, and secant, tangent. Cosecant, cotangent is exactly the same as secant, tangent. You just have a minus sign floating about, if you look at that, right? So sine, cosine have their world, and then the other four have their world, where we just have to be careful with the negative sign. Formulas that you need from the previous life are Pythagorean identities. If you don't know, so Pythagorean identity is the sine squared x plus cosine squared x equals to 1. But there are another 8 versions of this formula, because we can write this formula as sine squared x is 1 minus cosine squared x, and we can write it as cosine squared x is 1 minus sine squared x. So as you can see, it's already 3. I know it's just rearranging, but in some problems you will have to do that, and you will have to use maybe this formula, right? If you go and you divide through by cosine squared, you are going to get tangent squared x plus 1 is equal to secant squared x. Remember the pairing goes tangent secant? Well, there it is. And then the other 2 forms of this, which is tangent squared x minus secant squared x is equal to 1. And what else? Secant squared x minus 1 is equal to tangent squared x. And that's what I said. Please pay attention. -1, clearly. And if you go back to the original problem, and instead of dividing it by cosine squared, you divide it by sine squared, you have 1 plus cotangent squared x is equal to cosecant squared x, which gives you yet another 2 formulas later on. So cosecant squared x minus cotangent squared x equals to 1. And the other one, cotangent squared x is equal to cosecant minus 1. Cosecant squared x minus 1. Good. So as you can see, 9 formulas. But you see that I derived them all. Now, students usually memorize these 3, and then obviously if you have to use algebra to flip. But you have to keep your mind open that some of these are going to pop up here and there, right? So keep an open mind as they show.
So when cosecant square of x by cosecant square of x equals 1, you forgot negative. I'm trying to say.
Over here?
Yeah.
No, I moved this one to the other side, so it remains positive 1. Over here, I moved secant this way and 1 that way, so I did forget there. The next type of formula is the power reducing. I can't emphasize these enough. These are going to be central for solving certain problems. Sine squared x is, that's it. Cosine squared x is
1 minus sine 2x over 2.
Over 2, yep. Good. Gotta know this. That's it. Problems that have sine squared and cosine squared in them cannot be done.
Different when I have to go use like 1 minus cosine squared.
That's experience. Doing 100 problems. Like anything else. Right? Like driving a car, like everything else. Introductory example. This is the cheapest we can see. Sine to the 8x cosine x dx. This is done in Calc 1. You should know how to do this one already. Introductory example. What do we do here?
U sub.
That's it. U sub. What's U?
U equals sine of x.
Perfect. Go.
Equals negative cosine.
No, derivative sign is?
Cosine.
Yep. So a problem like that should take approximately 17 seconds to do. $20 seconds? Okay. The next integral of tangent x. So, what do we write? Very good. So u equals cosine x, because the du has to stay in the numerator with the dx. So we have integral of negative u to the negative 1 du, which is negative. Why are you saying negative? That's weird. So what's the integral? Plus c. So much enthusiasm. Minus ln of cosine x. Now, would you all guys agree that I'm not supposed to leave the answer like this? Because it's not pair. Thank you. It's not a pair. Tangent cosine is not a pair. So what I'm going to do is I'm going to take this negative 1 in front and bring it to the cosine. Cosine to the negative 1 is, it's 1 over cosine, which is secant. No, not the inverse. That's one of the problems in mathematics, because we have a notation for the inverse to be minus 1, and we also have the 1 over.
You write out what you were doing the entire time.
Do I? What happened?
You go write out what you did. I think you had that written down.
Yeah, we did. I know I did this problem. I'll write it. It's fine. All right. And now, I don't have a drum roll here, but here we go. This is the types of problems that we will be dealing with in this section. We are going to have exponents on both sine and cosine. So what you can get is 2 odd powers, 2 even powers, or a mixture. That should be common sense, right? If you have odd power anywhere, that's the easy problem. If you have 2 even powers, that's going to be the annoying problem. I can't label them as hard. I have to label them as annoying. Annoying because you are going to use power reducing formula to solve those. But if you have the odd number, you can solve the problem by peeling off from the odd power one of those, either sine or cosine. So as you can see here, I have sine cubed. So I will peel off one sine, which will leave me with sine squared, and I keep that sine for u sub. The other 2 sines I convert into cosines using the Pythagorean rule, and I can do u sub. So most of the thing that we're going to do in this section is going to be massaging problems where we keep the part of the problem for du, because we know in advance that that's going to be the du part, and the rest has to be transported into the other trig function that will be u part. So the first order of business over here is for me to write sine squared x cosine squared x times sine x dx. So this is the part which I'm going to set aside, and this is the one that I have to change here so that I can have everything in terms of cosine, so that I can say u equals cosine. So by Pythagorean identity, this becomes 1 minus cosine squared x times cosine squared x times sine x dx, which is the part that I am leaving aside, setting aside for my the du part. What happened? No, this Pythagorean identity is not power reducing. Pythagorean identities don't have divide by 2. Okay, those are these, right? So now I just distribute cosine squared x minus cosine to the 4th x times sine x dx, and there it is. So now it's easy. Negative sine x dx, and we put those negative signs everywhere. Well, here the negative sign will propagate, get negative u squared plus u to the 4th du, and the whole thing is u to the 5 over 5 minus u cubed over 3 plus c, and then I don't care about u, care about the x, right? Which is 1/5 cosine 5x minus 1/3 cosine cubed x plus c. If we have one or both exponents as odd, we set aside one sine or cosine for du and transform the rest. That is the entire method as soon as you see sine and cosine with the odd exponent. Now, obviously, if you have a single sine or a single cosine, you will do the basic u sub, right, immediately. But if you see sine to the 7th times cosine to the 9th, you see sine to the 3rd times sine cosine to the 4th. So as long as at least one exponent is odd, this is the way to do it. You peel off from that odd power. Now, if you have sine and cosine odd, You can pick which one you want to set aside. It's not a problem, right? You can pick any. But if it's one even and one odd, you are stuck with the odd one. That's the one that you have to yank out, and then the rest is just algebra, as you can see. So grinding through the process. The evil situation is with two even, which is where you have to do a lot of work. What happened?
When you had this sign after the cosine square that's and you got that out, like did you integrate that part and multiply it by
You're talking about this line?
Yeah.
I just did the u sub.
Oh.
This is u squared. This is, but I assume it's negative. So negative u squared minus a minus a plus, and then this whole thing, as you can see here, is du. So it's just a swap. That's the u sub part. All of these problems are manipulation and then u sub to finish it off. All of them. Let's do the cheaper example. Cosine to the fourth x dx. I can rewrite this one as the cosine squared dx. So do you see the nested? Do you see the nested power reducing here?
So we separate them out, be cosine square of x, cosine square of x,
Yeah, we can do that too.
and FOIL.
All right. So you hit with the power reducing both of these. Kick 1/4 out. And then FOIL. And then you notice that you still have one term that it's squared, power reduced again. So the higher the exponent, the more power reducing there is. So we wrote this as cosine squared times cosine square. You FOIL everything. You notice that foiling creates another one. And the usual mistake that kills the grade a bit is you forget that the input is 2x and it becomes 4x upon the second power reducing. Every time you do power reducing, it doubles the angle. So you look at the input, and if the input is already 8x, your next power reducing is 16x. So the first time you did the power reducing, it was just x, and it became 2x. So that was the first power reducing. And then once you FOILed, now power reducing goes from 2x to 4x. For that term only, these terms are just copied. We don't do anything with them, so they keep their 2x's there.
I honestly saw you did the quadratic, the memory said.
Yeah, I did quadratic. I skipped because, but you, if you guys have issue with quadratic, you FOIL it in a margin of the problem, right? Or you can do a squared plus 2ab plus b squared. No, you have to get the same answer. Just time for us to integrate. So we have 1/4. Integral of 1 is x. Integral of cosine 2x is sine 2x over 2, which cancels the 2 over there. Right? There is a 2 here that gets canceled with the over 2 that you get from the u sub. plus 1/2 integrated is 1/2 x. And then cosine is integrated is sine, so 1/8 sine 4x. Because you already have a half, right? You have a half, and then the 4 will be over 4, so 2 times 4 is 8. We can only combine x and a half x into 3/2 x. Plus sine 2x plus 1/8 sine 4x plus c. We should have plus c on the upper line as well. It's a limited edition. Awesome. The problem that I'm going to write here is what I'm going to ask you to do at home as the practice as you're learning this. The steps are the same except one of these formulas is going to have a minus because I'm going to ask you to do this at home. Sine squared x times cosine squared x dx, right? So do this at home. When you review your notes and stuff, you will run into this problem. Do it. It's going to have the same steps over here, except one of these is going to be minus, and stuff will work a little bit different for the answer, but the procedure is identical. So now, when we have only even exponents, when we have only even exponents, that doesn't, I don't like the order of the words in the sentence. If all exponents are odd, sorry, if all exponents are even, there we go. If all exponents are even, use power reducing. That's it. End. Now we go with tangent secant pairs. Tangent secant pair. I always start with remembering for the 50th time in this class that the derivative of secant x is secant x tangent x, and the derivative of tangent x is secant squared x. This is insanely important because if you are going to finish off the problem with u sub, and all of the problems are going to be u sub, these are your u's, and these are the leftovers for du's, which you have to set aside. So, need to set aside, because those are your dx handles for du. Let's start with an example. See you next week. The integral of secant to the 5x tangent x dx. So this is our first example. You have the choice. It looks like that both could work, right, for the moment. So you go and you say, all right, I could peel off one secant, and then I have secant tangent to leave aside, and then I have secant to the 4th left, so that's u to the 4th du. Oh, this works. Perfect. can I use the other one? If I set secant squared aside, it leaves me with a secant cubed, but the Pythagorean identity can only take even exponents, right? And you have secant cubed. So the second line cannot work on this problem at all. So what I'm going to do is I'm going to peel off one secant and leave the 4 on the pile. This is the part that I set up aside. So u is secant x du is secant x secant x tangent x dx. And now we have u to the 4 du, which is 1/5 u to the 5 plus c.
How were you able to cancel out the D? I know you said you reduced, so I'm just trying to figure out how were you able to cancel secant and x and tangent x.
I'm replacing it. See how this is this and this is the same? So I just swap as a block. I should use the word substitute, right? Because that's what we did. So how about secant to the 5 x dx? Any ideas? What happened? If we set aside secant squared, but for secant squared we need the tangents, right? But I don't have tangents, and what's left is secant cubed, which you can't use identity to change it to tangent. Yes? Yes. So we peel off one secant. So we have secant squared x, and the secant x dx. each one of these gets transferred into a tangent, and then when we multiply this one through, we'll have a secant tangent to work with. So this is 1 plus tangent squared times 1 plus tangent squared times secant x dx. And now we FOIL to get 1 plus 2 tangent squared x plus tangent to the 4th x times secant x dx. I need tangent cubed. I'm getting tangent squared. Tangent to the 4th. This one doesn't work actually that way. It doesn't work this way. Nope, 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 nope.
Yeah, if you do secant cubed, it looks like you can use about secant and then eliminate secant x tan x.
So leave it as a secant cubed. Okay. This is secant cubed. Like this. Oh, this gives us the secant cubed. But it doesn't help us, right? For the second one. Oh, it does.
Yeah, I was saying.
Yeah, then it's plus, and over here take a secant tangent. No, but it doesn't work. Because secant tangent is from secant, I don't have two tangents to go into secants. None of that stuff works. What happened? Over here?
No, beneath that. Yeah. So that line is the second integral. Instead of putting off a secant tangent, put it in secant squared.
But then I'm left with one secant that cannot be transferred into tangents, because you need secant squared to transfer into tangent squared.
I bet you're in this is like what you took that secant squared that you kill off and transfer that identity.
Yeah, and then you made the tan squared the secant.
Yeah, either way it doesn't work. I'll have to. I don't want to waste time in class. I'll have to actually work this one out when I'll work this one out. So I'll just put the star over here. I'm going to get rid of these lines. I'll work it out and I'll bring it so we don't waste time. I'm just gonna pick problems from the book because when I make them, they don't work apparently. I made all the other ones up so far, but let's pick up these guys from the textbook so we are guaranteed stuff that actually works fairly. Problems 31 through 44 are all involving tangent and secant. So let's see. Here is the first one that definitely works. Problem 34. It is the square root of tangent x secant to the fourth x dx. So that one is cute. Well, I used the wrong word. I could have used adorable, but I didn't.
The last one I did was like 3 parts. And I realized it's not even
Oh yeah.
Also, every time you said that the integrated by parts, or you said that CK cube is the maximum one, like it's the hardest one that you're going to encounter in time 2, you could just,
Integration by parts.
yeah.
So what do we do here?
You use u equals tangent x equals du equals secant square x. Separate out the two secant square x, secant square x, cancel out secant square of x, and do integration for secant. Then u to the 1/2, and then when you get 2/3, u to the 3/2, and you can do.
But you also have the two secants that you, right? Two secants are for
You
du.
can cancel one of them out because.
But the other one that stays has to be where?
It can stay on the inside pretty much.
Well, it has to be transferred into tangents first. So that's one. Okay, so that's good. So we have square root of a tangent, x, and then one of the secant squares becomes 1 plus tangent square, x, and then we leave with the secant squared x and then dx. So now when you do the u sub, you set tangent, right? Well, actually, let me simplify algebra first. So it's going to be a tangent to 1/2 x plus tangent to 5/2 x u equals tangent x du equals secant squared x dx is u to 1/2 plus u to 5/2 du, which is equal to u to 3/2 over 3/2 plus u to 7/2 over 7/2 plus c. That's that.
May I ask you, can I be able to like take out both secant squares of x and then did u is equal to tangent x, which would give me u to 1/2 and then cancel out the secant squares, but I can use that theorem 1 plus by tangent square x as means.
But you have two secant squares, right?
Yes.
And only one of them will cancel. The other one stays.
Yes, and then I use 1 plus by tangent square of x.
Yes, that's what we did, right? That's this part. So one secant squared is here, and the other one is the one that it's there. And then we distribute, and then u sub. All right, another one. Tangent cubed 4x dx. This is 35. So what's the only thing that you can do in this problem? Peel off one tangent x, right? And then hopefully by changing the other one to secant using the Pythagorean, something could happen. Don't forget this 4x. That's just there to further make things interesting. Tangent would be secant minus squared minus 1. So secant squared 4x minus 1 times tangent 4x dx. And now when you distribute, what do you get? You get tangent 4x secant squared 4x minus tangent 4x dx. You see that this one is easy, right? Because u is, right? And over here, right? All right. Oh, welcome to Calc 2, yes. So for the first part, we have u equals tangent 4x du equals 4 secant squared 4x dx. So I need a 4 1/4. For the second integral, I have sine 4x over cosine 4x, right? And then we solve each one of those. So these are independent derivatives now, integrals. Oops. One quarter u du minus, and over here I can just steal the answer from the other one. We know it's ln of secant 4x plus c, and then it has to be 1/4 in front because of the 4. So this is 1/4.
Why is it
The tangent.
Yeah, but then
But you transform it.
you
Didn't,
have to put the
yeah, he didn't pay attention. Hold on. Right, it is cosine.
Oh, okay, yeah.
And then this minus makes a secant.
I think we have to put the sign though, because I think there's already a negative.
Yeah, it was
One
like
minus the other. So when we jump to secant, we have to put the sign in front as well. So it's already a negative from the previous integral. Minus.
No, but we're not going to touch that. Leave it. Because the minus sign that is from the problem stays the minus in a problem, and the minus sign that was within the tangent created a secant. Great, right? Thanks for the vote of confidence.
I get tangent square 4x.
Like this. Let's see, which one?
Tangent square 4x. Supposed to be tangent square
one?
x. Yep.
Well, this is going to be u squared over 2, right, when I integrate.
Like what I did was earlier, I said u equals 4x instead of telling that u equals tangent 4x. I did u equals 4x a lot earlier and got du equals du over 4, and then I.
But that's only going to address the this part. You still have to deal with, right, because 4x and 4x, that doesn't address the trig.
I say tangent u, then secant square of u.
You have to have this eventually. Now, if you combine this into u, then it has to be tangent of u. But it has to be done all the way. Yeah. It has to be done the whole way.
That's why the u equals 4x and then
At the beginning.
yeah, and then add it.
Yeah, but it's still, you can get rid of the 4x there. It's just going to get 1/4. I usually don't bother with that because all of the formulas have 4 times the argument, that you don't have 1/4 in front.
So then you
But
change
you have to get the same answer again. You know, if you do that,
Like if I put it back in, u equals 4x.
right? U equals 4x. You have to bring it back because the problem was posed in terms of x. The answer has to be in terms of x. All right, next problem.
I can't wait for the awesome numbers my math lab is going to throw in all of this.
I can't even imagine. Maybe I should be better off not opening the homework.
I agree.
But then you will complain that you want to do homework, and then
Yeah.
And some donuts. Only get 2.
cosine. Ooh, you're gonna love this one. I think you're gonna love this one. You're not gonna love this one? I think you will. It's too much. Cosecant to the 10. Let's just bring it down a notch. So cosecant squared, yeah, with a 10 it's just gonna go forever. Cosecant squared x cotangent cubed x dx. No. One minute left, and then another 30 after that.
And then all of that is cotangent.
So is this easy or hard problem?
Hard.
Easy.
Hard. Trick.
What do you mean trig? What's the derivative of cotangent?
Cosecant squared x.
And negative cosecant squared. You have a you have a cosecant squared there, so it's just a basic u sub. Cotangent equal u, you're done, u cubed. You can look at this problem and you know just by looking at it that the answer is negative 1/4 cotangent to the 4th plus c. You just look at it. So the goal is by Monday, you look at the problem like this and you just say, oh yeah, clearly 1/4 cotangent cubed, right? One quarter cotangent to the 4th x plus c with a negative in front. You forget plus c. And this is when I stop with this because what's the next section? Trigonometric substitution. Which means that every integral that we are solving, integral is posed as x squared plus and then square root and so on. We transform that integral into a trig integral and then we unleash this section to solve it. So the next section is practicing this section by default, because every problem is converted into a problem that looks like one of these. So technically, in preparation for your exam, the time management, right, is do every single problem from 7-4, because the trig substitution is practicing both sections at the same time, where 7-3 is only doing trigonometric integrals. The other one has the transformation into the trig domain, and then you have to do trig integrals. So, in terms of time stuff, like for homework online, you do maybe 3-4 problems from this, just to say you have some percent there, so it's not 0, and then try to do all of the problems from trig sub, because in that way you are practicing both sections at the same time. So let's restart the stream, and I will take a look at the trig sub.